it's always human error, you know, most of the time.
Well, at least
All right, so let's see. Let's see what we're doing here. So we have this bumper, and we say that our force of impact, we assume that in the worst case scenario would be about 80,000 newtons, which if you divide by 10 would be about what? Would be about 80,000. That would be 40 times the weight of the car, no? That's a lot. So it's pretty pessimistic. But actually, you know, this type of problem, this is similar to what you do the design, or the way they used to do the design all times for the landing of the aircraft. You know, landing of the aircraft. You know what is the test, the landing test for certification of the aircraft? They bring the aircraft, I think 60 feet or 40 feet, no, 40 feet high, and they drop it straight down. And the aircraft needs to be able to sustain with zero damage the impact. So what do? They, you know, you never know exactly what will be the force of the impact, but now we could assume almost the problem for the springs to be, we could almost do now what, like 80,000 equal to 2kx, no? And see what will be the worst case scenario. But we're still gonna do it a little bit more fancy and see if we find something different. Okay? With the damping and so on. So model the problem as a force damping system. So basically we say we're going to take now, we could do it upside down, it doesn't matter, but let's say this one, we're going to have here our block F. Let me just do one spring here. That will be 2K, since K1 equal K2. Here we have our damper, C, and here we have our force. Doesn't matter if it's pushing in or out, so the spring will be the same thing, it will be F in. All right, so if you want, what should be the equation of motion? At impact, what could you have over here? 2K X, but we know the X is, let's say, should be equal to delta at the most, no? 20 centimeters. And then this will be the Cx dot. So write down the equation of motion, what would you have here? Summation of forces equals to MA. What would you have here? We have F impact minus 2kx minus Cx dot. Forgot to do another figure here. Will be equal to what?
MX double dot.
Mx double dot. So basically, we have the equation of motion, mx double dot plus cx dot plus kx equal to the, plus 2kx equal force of the impact. Okay, what can we do next? What would you do next?
Find an expression for the analytical solution.
Do we do that analytically or do we solve that numerically and see what happens?
You- If you can determine what damping the problem has, you could, if it's critically damped, then you can find C, and then you could plug in numbers for X dot, and X double dot, and then solve for K that way.
Say that again?
So if you could draw a motion graph, you could assume that it was critically damped. So that means the critical CC is gonna be equal to C, so you can solve for C that way.
So you solve for C from the, but I don't know how the time response is gonna look like because F impact is just equal to a constant.
Wouldn't it be though? Okay. I mean, you're assuming over that impact, that's the total. All of the behavior happens in that 0.5 of a second, right?
Yes.
So there's some, like it would depress and then come back. So wouldn't that be the motion graph then? It would start at some distance or start at 0, come up and then come back down?
Yeah, I mean, that's the way it should, but the way we have it now, we have F impact, no? So what about if we try to solve this numerically and see what we get?
All right, but you might need to make one more assumption because to numerically solve it, you're gonna need a value for,
C.
yeah.
Yeah, so what I'm trying to see is that then we can see what value of C, if it's damped, see what value of C will make it go down in about 0.5 seconds, no? For a certain value or something like that.
All right.
Let's just try to plot it and see what happens, okay? We might not get anything. So, all right, so let's go back now to, oops, I didn't put the computer, so we might have to reset all those things. Did I turn it on? Yes, I did. No, so we're good. So let's go to the computer. So, cancel here, home. This is not going home. No, computer. And another over here. So we're gonna go to MATLAB. Okay, so guys, the whole thing that I want you to realize is that when I'm gonna grade the exam, it's not that I'm gonna say this one is wrong or this one is right, no? It's gonna depend on the assumption and see how you're able to carry on your assumptions
All right.
to get to a result, okay? Like I always say, you give the same problem to 20 different engineers, 20 different engineers are gonna find different results, no? It depends on the assumptions. So maybe let's try to open a file that we have used already. So force damping, it should work.
Yeah, probably.
Let's see. So here we have, so let's first, before I do any mistakes, so save as, it's funny, example, same as exam. So exam 1, problem 4. But we might have to move this one somewhere else because we don't have the functions. ME400 somewhere like that. Folder, exam 1. All right. So okay, share. What's it that one now? Oh, MATLAB file. we find out, we copy then the other one. Okay, so M equal to what, 2000?
Yep.
Oh, we're gonna have to assume them values that way for K. Okay. And C, so, alright, let's say right now C equal to 1000, C equal to whatever, 10, and then we try to guess. So X1, I'm just gonna see if this is gonna run. T equals, we don't need to go that far as 60, so maybe let's take a smaller time step. And let's go to what is it, 5.5 seconds?
Mm-hmm.
So let's do 2 seconds at the most. And here we have ODE function 3. Oh, so the only one we know is really 2000. Okay, so maybe over here, so let's go to the camera. All right, let us try to give some initial values. What I call, let's do some educated guessing. Page 3. So educated guessing. So what could we say initially? So if static problem, what does that mean? X of the dot, now the acceleration velocity will be 0, so the problem will reduce to what? 2kx will be equal to the force of the impact, okay?
Mhm.
Where x equal, we said lambda, which was what, 20 centimeters?
Yeah.
So which is 0.02 meters.
No, just 0.2.
0.2 meters, correct. So we could say over here that then k would be equal to the force of the impact divided by 2x. Okay?
Mm-hmm.
So it would be the highest value we could get for k. So we can take something smaller, and so in that case, so the numerical value would be here. What would that give? K equals to 80,000 newtons divided by 2 times 0.2. So you get 0.4, which is 4 divided by 10. So you get 800,000 divided by 4. 200,000 Ks. What do you get for K? Is it 20,000 or
200,000.
200,000? No? That's what I thought. Wow. So 200 kilonewtons per meter. Wow, so that is a big value, no? So what could be our initial guess? Let's say for half of that or something like that, or
Sure, half sounds good.
so let's say initial guess, so first guess. Okay, initial to be half of it, so about 100 kilonewton per meters, and for the damping, what was the relation relating the damping to C? Was C over M equal to or the 2 sigma omega n?
It's just two.
I think, isn't it C over 2m omega n? That's what I remember.
C equals 2 omega n.
Why don't you look at the notes, because I don't have the notes with me, so that's why. Oh, maybe I had it on my, hold on one second, maybe it's on the, I think it was on the file, no? Here?
Okay, I've got C critical is 2m omega n.
So exceed, so, okay, so we have the damping is equal to C over 2m omega n.
Yep.
All right, so C equal to 2cm omega n. So let us assume at the beginning something pretty large. Let's assume this one to be equal to 0.5, okay? I don't know, we need to start somewhere, no?
Mm-hmm.
So first guess. All right, so that's what I will do here. Okay, dot com. So basically, let's go for that and see what happens. So we might have to change home computer. All right, so what do we say we're going to do over here? So we need to do this the other way around, no? We don't know C. We're going to assume, let me check this one, so it's just psi. So psi equal to 0.5. We say this one was going to be equal to what, 100,000
Yeah.
kilonewtons, 2,000. So this will be, so we need to do this the other way around. So that C will be equal to what? 2 times psi times m times omega.
In the xi, under the third one down, you have a 1 instead of an I.
On which one?
The third one down from the under example.
On the example, 1, 2, 3,
Yeah.
oh, okay. So the C, we can eliminate this. Omega t, we can leave it, t, whatever. So initial, yeah, we need an initial for this positive t function 3. Okay. So what do we need from the function of 3 here? We need 2,000. Oh, 100,000. And this one we're going to have to calculate it, no?
Mm-hmm.
Otherwise, we need to put this stuff as well on the other side.
Yeah.
Omega. Omega, what else do we need to put? Oh, these two lines.
For omega, should it be the square root of 2k over m since there's 2 springs?
Yep. Did we say that? Wait, was that for? Yeah, but be careful because what did we write down for the assumption? That was already for the 2K, no?
You mean the 100,000? I don't think so, was it? No, that's k just 1, I think.
Wait, let's see. Let's look back. Let's look at
Yeah,
it.
check.
So we say here that here we have it with 2K, no? Yeah, here we have it with 2K. So the 2K must be equal to 100,000, or is it each one?
No, each k is 100,000.
So each K is 100,000. Yes. So yeah, we can keep the 2K on. It's not that easy to do. Computer. All right. So 2K. Let's not forget the 2K here. And then we need to change here this, no?
Mm-hmm.
If we put a constant value, what is that gonna do? I don't know if it's gonna do anything. Because, but what we can assume is that it's equal to a damping, and we can just look at the maximum amplitude, no? If it doesn't solve it, let's say.
Yeah,
So we need to put a 2K here as well, no?
should be.
2K CM. What? Let's see what happened. Okay. So what happened here? Oh, exceed line 12. And what is it?
It's.
Yeah, it's side only. This one here. So it's gonna be the same on the other one, no?
No, I don't think you copied that line.
Okay.
Hmm.
So that's not bad. That means that it done very quick, no? That's not a bad figure. So maybe it's too stiff over here. I mean, we can maybe change the time to go to 0.5 and see what happens. But basically, we see here that it wants to go to 0.4, no?
Mhm.
Which probably is a static deflection. Huh. So let's change this one to 0.7. So I like this one, but I don't like this one, this figure. Because this basically is telling you that it's gonna go to the, probably the 0.4 here is the, whatever value we get for the force divided by the x, no?
I think we need to change the T-span also in order to see that graph better.
I think it's convergent. You want to put something smaller?
The T-span, because we changed T but not T-span, and for
Oh.
the second figure, it's referencing T-span.
Okay, yeah. Yeah, I don't even think we need this one, to the truth. Oh, yeah, for the figure.
Oh, it's much better.
So this one now is, you see, it's going down, but then it's gonna go to 0.4, no?
Mm-hmm.
All right, so let's assume something here.
Flex too much.
Yeah, let's assume one thing here. So let's assume this one will be times cosine. And you do something, what is omega on this one? Any idea? Should be pretty stiff. Then, a nice value.
Yeah.
Let's say we put 10 over here. Okay. Okay, so by doing this, if we add here the cosine function, what are we assuming?
That the car is repeatedly smashing itself into the bumper?
Can we look at it that way? But I was looking more about that the forcing function will take the shape of the cosine. So initially it will be very high at the time of impact, but then it will start decreasing. Yeah, but I don't think that's a very good assumption. So what can we do over here?
What if you made it exponential? That might fit the realistic situation a little better.
Yeah, because what happens is that really the force, okay. I think the way to solve this problem would be just to give, what about? Okay, because really the force is not constant. The force we can assume it would just be for an instant at the time of the impact. So it's not all the time. So is it a way for you to transform that force? So what would be, go ahead.
If you just model it as an initial velocity.
Correct,
And
that's
then
what-
use the acceleration.
Correct, so basically we assume this as being a damped vibration of a free vibration problem, and the force will be put into an initial condition. Is that what you're saying? The step is that how do we put that one into an initial condition?
If you just remove the forcing function and set V0 equal to 20.
So we put here, so the forcing point we put 0,
Yep.
okay? But then we need to go here to the initial conditions.
Yep, and if you set V to be
So this
20.
one to 0.2, and this one to equal what, 0.4?
Why is the initial velocity 0.2?
No, I don't know, no. 0.
Shouldn't
I
it
was
be
just trying
20?
to think about
Initial
No.
velocity would be 20.
Yeah, the initial velocity would be 20 because that's the velocity of the car.
Correct, so 20. And the initial here,
0.
0. Could probably get away with it.
0 over here.
What would it be the point, whatever that is, 0.5?
Well, let's try, I don't know what's gonna happen, no
20.
idea.
Centimeters? I don't think so, because that's the max deflection it can absorb, so that would just be the max amplitude you're looking for.
Okay, yeah, so that's better. So it looks like if we have these values, it will get damped out in how much time? Less than 0.5, no?
Yeah.
Yeah, more or less.
So what we can do now is maybe change the value for K.
And until you squish that
Until
deflection
we kind
under
of,
0.2.
yeah, we can probably do a loop program, you know, like loop while this one, but you see what I mean?
Mhm.
We could do a loop, but let's just do it here. Let's just go through another guess. So that was our initial guess, but could be our second guess. We can make it smaller. So let's go to 50, see what happens, and then we can go back up, no?
Mhm, sounds good.
So that one looks about right, no? I don't know why it's not doing the line here. Does it look like close to 0 here or no?
It's close to 0.5, yeah.
Maybe it's a little bit more, no? I don't know why it's not doing the lines, it's not doing the grid on, I have no idea. Maybe tools, edit plot, I have no idea, I don't want to edit that one. Tools, edit plot. Can they put the lines on here or no?
On, I think under tools they might have had a grid thing.
Grid is on here, supposedly. So maybe, but maybe there's a tick for the.
Oh, the grid is white, perhaps.
Oh, yeah,
White.
that might do it.
So this one here?
I think so.
That might just be the color of the
Oh, no,
background.
that's the plot itself.
So grid, box, axis. So how do we get out of it here now? So I'm gonna go back to the previous one here. Any idea? Grid. Let's see. That's what I thought. Not doing anything. So we have this one 0.5 is here. I mean, I think it's more or less 0, no? It doesn't matter. I mean, I
Pretty
think
much,
we're just going
yeah.
through the process. Okay? We're finding the solution. So we can say that, let's go back over here. I know this is not perfect solution, okay, what we are doing. If I had a bit more time, I could do probably, I mean, let's try to do it, but the thing is that we have this function over here. Yeah, it's going to be difficult to do this within the function because we could do a loop saying change the values for k now. But then how do we change the value of k within the function? You see what I mean? So that might give us some problems, so let's not try. All right, so let's just go back over here. Cam. So, using the MATLAB code, it was determined that for K approximately equal to what, 50,000 kilonewtons per meter. And I mean, another thing to do would be to see what would be if we change the damping ratio, no? Because here we did one assumption for the damping ratio. All right?
Yeah.
We use what? So probably we use the damping ratio to 0.1. We might have to use a higher value for this, no?
Mm-hmm.
Okay? But let's say for this assumed value, we find out that the response get damped within half a second. Okay? But again, if you assume a different value for the damping ratio here, then we'll have a different response for the K, no?
Mm-hmm.
Probably. I mean, 0.4 is high, but it's not that high. So it's basically, we could say it's 40% damping.
Mm-hmm.
Probably those dampers have a much higher value, I guess about even 70 or 80, no? The ones would be for, so if you have a 70, 80, probably you can take them down the value for the stiffness a lot more. Okay, let's try one. I mean, let's try one. Let's say, since we are here, computer. All right, so I don't know, what do you think would be a good damping value for this type of products? Oh, we put 0.5, not 0.4. 0.5, sorry. So what do you think would be a good damping value?
I have no idea.
I assumed critically damped.
It is what?
I assumed that it was critically damped.
Yeah, but critically damped, what do you assume for the, so it's higher than 1.
No, it should be exactly one.
Exactly one.
So you want to put 1, so you assume 1, okay? So that means we go exponentially down. So probably here, let's just
So
run
you
it.
need to change it there.
Change it here. Probably then the K is way too high, no? But, oops. Let's just run it here.
Mm-hmm.
Looks like it's worse.
Well, then all you'd have to do is adjust the K value until the maximum deflection was under 0.2.
Yeah, but why didn't it go down faster than 0.4? You would assume that it will go faster to 0, no?
Well, the thing is that on the other one, even after it passed 0, it was continuing to oscillate because it was going into negatives. Here, once it gets to 0, it'll stay there.
Oh yeah, it's exponential. From here it's
And
exponential.
the problem doesn't say that you have to have it stop in 0.5 seconds. It just says it can't deflect more than 20 centimeters in that 0.5 seconds.
Correct. So, yeah, so really we should just look at 0.2. You're right. So this one will satisfy that condition, no?
No, not quite. It needs to have a
Yeah,
smaller
I know.
peak. But all you have to do at that point is just trial and error with K values until you get there.
Yeah. Yeah, you're right. So, yeah, I was looking for 0. So then the one before, we could even take a lower value, no? So for here, let's say we put K equal to 60, I think that will probably work. Does that one work now?
No. Looks like you're going to have to bump it up quite a bit.
Almost, but not that much. Almost.
Actually, that might be a little,
So what, 75 or whatever?
No. problem isn't saying that at 0.5 it has to be 20 centimeters, at least as I read it. It sounds like it cannot be greater than 20
Than 20 centimeters,
within
yeah.
that interval.
Yeah, like you can't go past 20 centimeters.
Yeah,
And
so,
then by 5
so we would have to raise the K value quite a bit.
Yeah, to like 100, maybe.
You
Yeah.
think that much more?
I don't know, when I ran the problem, I got somewhere in the meganewtons per meter.
Now it works.
Well, the thing is, I don't know, maybe I'm reading the problem wrong, but the way I read it, it doesn't sound like the value at 0.5 seconds has to be lower than 0.2 meters. It sounds to me like in the interval from 0 to 0.5 seconds, the distance can't go any further than 0.2 meters. So, I don't know, like I said, I could be reading it.
I agree, I agree with you, that's what it is, but what happens is that the stuff you see over here,
Mhm.
I don't know if it's really the real deflection or if it's, from the initial condition.
Well,
So you will say, so basically you will say, yeah, I see what you're saying, so you will say you have to go literally on the 100, so it stays all the time on the
yeah.
0.2. Okay, that's another way to look at the problem, yep. Yeah, we
Much
need to
closer.
go. Is it all the time the same thing, goes here to 0.55, no matter what we do over here, no?
No, it's
Last
been-
time I went to like 9.
Yeah, it's been dropping.
So 275. It must be a way to change the value within a function, huh?
Might have to use an input or something.
I just had it bring in the values.
There must be a way to do this so we can do it, so. Yeah, it went down. Okay, so basically we do it that way, then the K must be extremely high, no?
Yeah,
We do that way.
or at least that's
It's
how I got
almost
it.
at 0 at 0.5 now.
Yeah, now it's almost at 0, but.
What you got for this?
Mine's wrong, because I messed up my initial.
All right, let's take that, literally, what value you wanna guess then, 675?
Sure, why not? Sounds like fun.
Okay, let's see what would that be really, now I'm curious.
Yeah.
Oh,
Much better.
Much better, so,
Almost there.
Definitely at 5.
so you guys the value, because I'm not the,
I'll give you the one I got and just see how it goes.
okay?
Be 1,353.
What about 150, okay?
Sure.
But this is 1,000. So remember, we multiply here by 10
Yeah.
to the 3, so.
Yeah, I accounted for that.
So, yeah, looks forward.
So it looks right about right, yeah, so. Yeah, if you did it your way, this is, looks about correct.
Assuming that was right.
So 1350. Okay?
Mm-hmm.
So if you want, let's change in the solution here, computer. So basically, let's do your assumptions. So this should be about, we kept the damping tool, so let me erase this part. And what are we saying is that following your recommendations, oops, so basically what I'm saying is that assuming critically damped, which means psi equal to 1, and 2, response must be lower than 0.2 meters during the time interval 0 to 0.5 seconds. Okay, it is found that what? K approximately equal to 1350 kilonewtons per meter, no?
Mm-hmm.
Okay? And I can attach the MATLAB code later on if you want. So 1, 2, 3, 4, 1. Okay, so we still have about 15 or 20 minutes, whatever you want to do, guys. You want to look at another problem quick?
How about the second half of number 3?
I don't know what number 3 is. I can bring you here. So this is number 3 over here. Okay, so number 3, I guess number 3, I think what you're asking is this. So when reading, I'm getting what you're asking me is this part where I say, knowing that the natural frequency of the above system is 10 Hertz, and that the amplitude of vibration is reduced by 60% in 10 cycles. Okay? Determine K and C. So the way I read this is that let's say this is 1. So you need to go through 10 cycles, so I'm not going to be able to do it right, but you start at 1, let's say. So it will be 1 cycle, no?
Mm-hmm.
Two cycles. I mean, I'm probably not going to be able to do it, but if you keep doing this, okay, so I know it's not going to be 10, but 3, 4, okay, blah, 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 to this one, that you will get here on this state cycle, the vibration to be 40% of what was initially. Okay? And you know that the natural frequency of this system is what? Is 10 Hertz.
Mm-hmm.
So all this is to find what should be the damping ratio. Okay?
Mm-hmm.
Actually, I was asking about how to find C.
Yeah, but that if you, I mean, what I'm asking you is that from here you can determine what is this, no?
Mm-hmm.
And once you have this, we should be able to find the damping ratio. What was the relation? Psi equals to M, was it C omega n, or was it the other way around? It was the other way around, no? C equals to psi M omega n.
Yeah.
Yeah.
So basically, omega n, you know it, you know m. You need to find what is this, what is this damping ratio, and you can find, you can estimate the damping ratio from 10 cycles. So then you need to use what, the logarithmic decrement equation, which was what? I don't have my class notes, but what was it? Remember we had log of x something, x1 over x2 equal to one expression?
I think so.
I mean, I might go, I'm sure I have them saved on the computer, but, so home, computer. So I'm sure I have the class notes saved somewhere. Let's see see ME400, course material. Okay, at least my intention was in here to make you go. I have to go too far to go. This is 1 cycle equals 2 pi 1 omega. Things right after this. Things right after this. Okay, here, no?
Yeah, that looks like it.
So using this relation, the logarithmic equivalent can be obtained from this one. So this is your ratio that you want. All right? So you put here the whatever x1 will be 1, this will be 0.4, and you can solve, so you have this ratio over here, no? You can solve for what will be psi. What will be c. Does that make sense or not? Okay.
Essentially.
Let's do an example very quick and then we'll stop over there. What I will do for this, probably I will go, I don't know if it's complicated to do it by hand or not, but just so we can go faster, so it's 2 pi xc, okay. So probably what I will do here, without thinking too much, I will say, I will make it bigger afterwards, okay? Restart, then we have the ratio, which is the log, let me just call it the one they call it here, delta, no?
Sure.
So we have delta, we know the ratio, so it will be, I know it's not going to be equal to that, but let's say it will be, I don't know if we use I don't know if they use they have this over here, so let's say it's 1 divided by, so what's x2 over x1, no? x1 over x2, okay. So 1 over, let's say, 0.4. I don't know if it's going to do that or not. Okay, so it kind of does it. All right, so I need to use now the relation. Let me do it symbolic and then we'll put values. I will do delta minus two times pi times c divided by the square root of 1 minus c squared. Why is it wrong here?
Is it because it has a square root on the bottom?
What do you say is invalid function?
Maybe, the semicolon in the denominator probably doesn't want that.
Oh, yeah. There we go. And now I will say solve the equation for psi. So you have two roots, and I will take, where is it? Yeah. So you will solve one of the roots, no? Probably will be this one. Okay?
Mhm.
We should say here, psi equal to this. And now you could just put the values. You say whatever. What do we calculate for delta to be equal to log? I'm just doing, okay, this one, but it might be different, no?
Mhm.
0.4. And what big psi? I don't know if it's going to transform, but so 0.14430. Does that answer your question or no? Okay?
Wouldn't that just be for one period, not 10?
That would be for, well, I think that is that.
Yeah, actually it would.
Yes, that would be for one period. So what you need to do then is to extend this to, so the expression for any period will be this one here. But you put this one, you divide by 10. You see this one, you can do this one divided by 10, no? So you can use this expression. So we could still use this one, will be, delta will be 1 divided by 10 times this expression. Okay? So basically 0.0145, which is more reasonable because that one was about 10%, no? This one is what, about 1.4? Okay?
That's actually what I ended up getting fixed out.
Yeah, when I put the problem, that's a little bit what I had in mind. So since I have the equations here, let me just go back here to the camera. So let's see, so what was the expression we had over here? Delta, which is equal to 1 over j log x1, x2 is equal to, what was the expression? 2 pi, was it 2 pi or 4 pi?
I think it's 2 pi psi. I think that's
2
how.
pi psi divided by this, okay? Where j will be 10 for the number of cycles. You solve for psi, and we're getting the expression for psi to be the delta divided by delta squared plus 4 pi squared. Okay, which was given in this case for 0.0156, let's say. Okay? All right, you want to look at more problems, or you want to stop and? Okay. So let's see what would be the other problems, and let's see what would be the major problem. So, so basically this problem, oops. Okay, so in this problem you need to find the equation of motion, all right? And knowing the mass and knowing the equation of motion, knowing the mass and the frequency, you should be able to find what should be the k, no?
Mm-hmm.
Okay? But you first needed to find the equation of motion for this problem. Okay, so you find the equation of motion for this problem, you find k, and you find c the way we just did.
Mm-hmm.
Okay, so I think this one is done. Problem 2. I mean, these ones are long. Did you have any problems finding the equation of motion of these ones?
Yeah. Number 2 I didn't have any problems with.
Basically here, if it was any trick, what is the trick? Is that the displacement of the spring is not the same as the one of the mass, no?
Yeah.
Yeah? So how do you find the relation between these two? You need to look at the angle, no?
Mm-hmm.
All right, so that's will be the only one for this one. Problem 1, I think we kind of did it in class, this one. We did a bunch of stuff in class.
Yeah, we did something very similar.
Yeah, it's kind of similar. The deformation of this one is going to be twice as the one of pulley A, no? Because when this is moving 1,
But isn't the fact that there's a spring on B make it different than that? Because B is not in pure rotation anymore.
yeah.
I think it should be
Yep.
twice A plus twice B.
Yes, that would be correct.
Yeah, so basically it would be twice plus whatever A sub B is moving, no? No. Yeah, I haven't done this one, so. Yeah, no, and so the information of this one will be half of what is going in this one plus X plus B, no? Is that what you said?
Yes, essentially.
Okay. Was the equation, did the equation at the end look very ugly, or was it acceptable?
For me, it was just long, not terrifically ugly.
Okay. So we'll have to do it, otherwise we can do it sometime, okay? All right, so let's stop over here. I think unless you have more questions about, more specific questions about the exam.
No, they come on.
Is that okay? All right, so have a good weekend. See you Monday.
Yep. Have a good one, Professor.
You as well.